So the first topic that I want to discuss is maximum likelihood estimation versus maximum priority estimation. So already know that we were interested in learning target function that was fx given fx and that x was mapped to some concept or function or some value y, and y, let's for example in whole discussion throughout this lecture I will be assuming that x is a vector and x would have, let's say, m components or d components, and each component would be binary. So and y is also a binary vector that could have values 0 and 1. So generally we were interested in learning functions that map x to some y. We can more generally learn probabilistic functions with uncertain outcomes and that can incorporate prior knowledge. So rather than learning functions directly, if we would have we will be learning probabilistic functions like what is the probability of y given x. So we can learn this kind of form. Given x, what is the probability of y? And if, for an example, if I want to predict two classes y equals to 0 and y equals to 1, I will give x to this probability function and I will calculate the probability y equals to, what is the probability y equals to 0 given x and what is the probability y equals to 1 given x. Whatever the probability is higher, I will assign my x to that label. So the most common approaches to estimate this probability was maximum likelihood we have discussed so in detail and maximum priori estimation. What is maximum likelihood estimation? So this was the total bias based theorem. If you remember that what it was like, probability of theta given d equals to probability of uh, d given theta and probability of theta upon probability of d, right? So we are only interested in this part in maximum likelihood. So this is like we want to maximize this portion. This is known as conditional, this is known as data likelihood function. So we want to maximize this data likelihood function for a given theta. What is the value of that theta which will maximize my data? That's what I'm explicitly looking in my maximum likelihood estimation. So this is the only thing I am going to consider. This is probability of d given theta, and I'm looking for that theta which will maximize this term, right? So for an example, what we have taken that we have taken one example. For an example, I have a coin and I will flip that coin. That coins have one side head and one side tail. So I don't know what is the actual probability of having head. I assume that the actual probability of getting head is theta. Let's assume that, and we don't know in actual what it is, but for to consider to write something into parametric form, we assumed that there is some true theta. That theta is nothing but the probability of getting head. That is true probability, but actually I don't know what is the true probability. I want to estimate from the data. So what I have a data. That data is having alpha 0, this having some heads, and head count is alpha 1. And there are some counts of tail. That count is denoted by alpha 0. So I have some n flips of coin, and n flips of coin means there are some heads and some tails. So the sum of alpha 0 plus alpha 1 is, let's say, and if I have flipped my coin n times, so there are alpha 1 heads and alpha 0 tails. And now I want to estimate it. So in very general sense, for an example, I have 10 heads, 10 flip coins, and 8 I am having heads, and twice I am having tail. So what is the probability that what is the probability of theta? What is the probability of x equals to 1? So in this case, by maximum likelihood estimation, the probability is 8 by 10. 8 by 10 means 2 plus 8, right? So it is 8 by 10. So it is 0.8. So by maximum likelihood, for getting my heads, getting my head by maximum likelihood estimation, the probability estimate is 0.8. So how to calculate, how I come up with this 0.8? Now I'm going to discuss that point. So let's assume that this is a Bernoulli random variable for coin toss. So I tossed my coin n times. In that n times, I got alpha 1 times my head and alpha 0 times tail. So if I want to calculate the likelihood function and all are identically distributed, it means first I get head, second also I get head, let's say third also I get head, fourth time I get tail. So this is the probability of tail, 1 minus theta, because it's a binary variable, right? What the prob If the probability of getting head is theta, then the probability of getting tail is 1 minus theta. Let's say this is my first toss, second toss, three toss, four toss, and fifth toss I also get tail. Now what is my data likelihood? So data likelihood will be the multiplication of all these terms. So that will be theta cube 1 minus theta square, because I get three heads and two tails. So that's why I come up with this expression of data likelihood. Similarly, if there are alpha 1 heads and alpha 0 tails, so I come up with data likelihood function is, my data likelihood function will be theta alpha 1 into 1 minus theta to raise to the power alpha 0. This is very trivial, right? Now you want to find out what is the value of that alpha theta which maximize that function. So it is very straightforward. We know that this is a function. The function is, let's say the function of theta is theta alpha 1 1 minus theta alpha 0. I want to find out what is the I want to find out the max of this function. Let's say this is a parabolic function. So I want, and this goes here theta. So this is my function value f theta. I want to find out with that value theta where f theta is maximum. So this is my theta, right? So this is my required value that increase my function theta to the maximum value. For an example, if I have taken this theta will give me this function value, which is not maximum. This is the maximum value. So I want to find out. This is a very straightforward thing. I will take the derivative of this function and put it equals to 0. So, but rather than taking the derivative directly, I am first taking the log of this function. If I take the log of this function, I can write this ln p likelihood, probability of d given theta, and then I'm finding out what is that value of theta which is maximizing this function, and I'm saying give me that value. So give me that value. So this is how I'm writing it. I'm differentiating my log likelihood function with theta, and this is my function, and this is log. When I take when I expand the log, you know that if I am taking the log of x square, it will be n log of x square will be 2 ln x. This 2 goes here, right? So likewise, this alpha comes here, and this alpha 0 will come here, and log will get converted, product will get converted into addition. So that's how these terms get expanded. Once I will differentiate it, log theta means 1 upon theta. So log theta means 1 upon theta. This alpha will come directly, and the log 1 minus theta will be 1 upon 1 minus theta, and when I differentiate 1 minus theta with respect to theta, I got minus 1. So now I will put this expression equals to 0. After evaluating it, I found that the theta is equals to alpha 1 plus divided by alpha 1 plus alpha 0. So this is the maximum likelihood estimate. So every time you give a data, if somebody gives you a data set and asks you that there are 7 heads and 3 tails, 7 heads and 3 tails, because you already come up with some formula that how to estimate the theta with maximum likelihood principle. It is saying that you just divide by 7 plus 7 by 3 equals to 7 by 10 equals to 0.7. So maximum likelihood estimate for theta, true theta. So this is, you can assume that I am estimating, right? This is not a true theta. So this is my true theta. This is my estimated value of theta. When I calculated my estimated value of theta by maximum likelihood principle, I got 0.7. Right? What are there any some questions? How point estimation in Bernoulli random variable is related? Point estimation? I'm not doing any post point estimation. I'm doing probability estimation here. Right. So there is one question how we are saying that the theta will produce a data set. Theta will produce a data. There will be some probability of right. If I'm saying there is a coin, if I'm saying this, so there is a question, but how are we saying that the theta will produce the data set? I don't understand this question, but let me explain what I understood. Let me explain from that perspective. So there is a coin, right? So it is having one side head and other side tail. So when I toss it, there will be some probability that if there is no bias in it, then there will be chances 50% I will get head and 50% tail. So this is the theta here, and my theta value of getting head is here is 0.5. But let's say there are 70% chance I'm getting head. So when I'm there 70% chance getting head, so it means there are 30% chance of getting tail. It means the theta will be 0.7 here. So there will be definitely there will be some theta. I don't know what kind of question is this. How we saying that the theta will produce the data set? So there is another question. MLE can be used for multiple variable as well. Yeah. It's just a simple expression I am taking to try and tell you that how we are calculating the maximum likelihood. Obviously, every estimation technique can be used for multivariate because in actual real world we have always a multivariate data set. So let's go to the what is maximum a priori estimation. So in the maximum a priori estimation, how it is different. We were in maximum likelihood estimation. I was trying to maximize this expression, but in map estimation, I am trying to maximize this expression, the product of these two terms. Right, this is what makes the difference between map and MLE. This is a prior value of theta, and this is my likelihood. So what I'm saying, I just maximize, and you can write it like P theta given D. So P theta given D can be written as P of D. What I am saying, I have to maximize this function. What is the value of theta that maximize this value? Because I am calculating with respect to theta, PD is a constant in terms, so I can ignore it. So what I will ignore this function. So finally I will left with this function. So this function in map I am maximizing this function, and in MLE I am maximizing only this function. So this is the difference. This is the extra factor in it. I'm again and again repeating this sentence because you should understand what is there. In maximum likelihood estimation, there is no prior estimation. I'm just maximizing this term only. But when I'm talking map, I am maximizing the product of prior and likelihood. Don't forget it. So the prior here, what I am considering, I am taking the conjugate the conjugate function. Conjugate function means that every time if let's say I have a prior probability p theta, and this is my likelihood pd given theta. So if I have some form of function, when I multiply this with this function, I will get the same form of function. So if this has a form of function, let's say this is theta beta minus 1, 1 minus theta beta 0 minus 1, right? So this is having this prior is having this form of function. When I multiply with likelihood, I will again get the same form of function. Let's see what it means. So here I am using prior, my beta prior, because it's a prior conjugate. Prior conjugate means that the form I am using in the prior will also get in my posterior. So this is my, for example, this is my likelihood, right? And this is my prior. So when I multiply by prior, this is theta beta 1 minus 1, 1 minus theta beta 0 minus 1. When I multiply it, what I will get? I will get theta alpha 1 plus beta 1 minus 1 into 1 minus theta alpha 0 plus beta 0 minus 1. So this is the same form, right? Here I am having some power of theta and some power of 1 minus theta in my posterior. and here also I am having some number of theta and some number of 1 minus theta in my prior. So this is what it is called prior conjugate. Every time I multiply a prior with some my likelihood, I will get the same form what it was in prior. So this is known as prior conjugate. So this beta function is a prior conjugate in Bernoulli distribution, or binomial distribution, I would say. So don't forget it. So I want to maximize this function, right? So I want to maximize this function. So this function is, this likelihood function is this theta, and this prior function, this function is this. When I multiply it, I will get these two terms. I just shown you in the back slide. This is a constant, I can ignore it. When this is a constant, I can ignore it. I left with these terms. This term is simply my maximum likelihood. When in my MLE, what it was theta alpha 1 minus theta alpha 0, right? And what it was alpha 1 upon alpha 1 plus alpha 0. That's what I found from MLE. So it is also in the form of MLE now. But so the maximum, so what will be the value of theta that maximize this function? It will be alpha 1 plus beta 1 minus 1 upon alpha 1 plus beta 1. This is written here, right? So this is same thing. So the difference, what is the difference between MLE and a map here now? So the difference is that in MLE, for the same parameters, I got alpha 1 upon alpha 1 plus alpha 0. This was my MLE estimate, and this is my map estimate. So there is a term, extra term here is beta minus 1 in the denominator, and these are the extra terms. Extra terms are like what my assumption it was. For example, I would have said that my assumption was that the coin was fair. If the coin was fair, I would have assumed that there would be 50%, 50 heads and 50 tails, right? So in that case, beta minus 1 will be 50, because my prior assumption about head and tail was that, let's say, 50 heads, and similarly I have 50 heads again, and this is 50 tails. So this is my 50% prompt assumption. But if I am saying that there are 10% head and 50% 90% tail, so let's say I can vary this function like this. So this is what we mean by there is a difference between MLE. In map estimation, we have a we assume imaginary heads and tails also. I already discussed in a lot of detail. I don't have to go it again and again, because if I will go through this like this, I will not complete the revision. So does beta mean it is a count of say heads and tails from the prior experience? Like, yeah, exactly, sir. So does that beta means count of say heads and tails from the prior experience, like we have alpha values for current data set? Exactly, you're very correct. What is beta? It is so the question is, what is beta? What is this? So this is constant, normalizing constant. Like in normal distribution, we had 1 upon 2. Like we had in normal distribution, we had 1 upon 2 to the power pi variance square. So this is just a normalizing constant. Why prior knowledge is represented sometimes using gamma and sometimes using beta? What? It's just a notation. So there is one question, why prior knowledge is represented sometimes using gamma and sometimes using beta. So this is just a notation. You can take whatever you want. Every symbol what you feel that I want to represent my prior by this symbol, you are free to do that. Nobody is stopping you. Don't get stuck. So there is one student who is continuously bothering about what is this beta b0 comma b1. So don't get stuck here. Just ignore it. That it doesn't exist. Like it is a constant n. Ignore it like it's a constant number. Okay, you are talking about the beta distribution. So you are talking about this. I don't get this question, right? So there is one student continuously asking what is this beta 0 comma beta 1. So you are talking about this thing or this thing. You be first you should be very clear. So this is a beta distribution thing, and this is a normalizing constant. Ignore this as it doesn't exist. You don't have to bother about it, and you need to care about the denominator, numerator. When you multiply numerator, you will get this expression, and you will maximize it. Okay. So there is another question, another important classification was, so far I have discussed what is the difference between MLE and MAP, and now I'm going to discuss what are generative classifiers and discriminative classifiers. So generative classifiers first. So generative classifiers means that so generative classifiers means that I have a same function like what are the p x given y, how to estimate that. So there are a number of ways to estimate this probability that a given x, what is the probability of y. So there are a number of ways. So one number of ways how to estimate this probability by generative classifiers. In generative classifiers, what we do, we have some prior probability. We estimate prior probability. Then we estimate the likelihood probability. So if you just to recall that the probability of A given B into probability of B is nothing but the probability of A given B, right? It's a joint distribution. So when I multiply prior probability with likelihood probability, it is nothing but I am calculating my joint distribution, unnormalized joint distribution. So by this I mean to say that when I have a complete joint distribution, just recall that chapter when I was explaining joint distribution. Joint distribution means that you now know that everything, if you have a joint distribution, you can estimate any probability whatever you want. Even if you want to generate some artificial data and you know what are the parameters of your joint distribution, you can artificially generate some data. What I mean by artificially generate, for an example, now you know that your distribution of probability of head equals to zero point 0.7 and the probability of tail equals to 0.8, the zero point 0.3. This is what you know. Now what you can do, you can generate random data set using this estimation. What you can do, you can take a uniform distribution, a uniform, you can generate a uniform number, and let's say that number you generated from 0 to 1. Every time the number goes, the numbers come greater than zero point 0.7, just mark it as head. Every time it comes less than sorry, every time it is like up to zero point 0.7, mark it as head, and every time it falls into this section, mark it as tail. So this likewise you can artificially generate. So what I am trying to say here, when you are using generative models, you are in that model you are calculating two things: prior and likelihood. Prior and likelihood is nothing but the estimate of a joint distribution, and if you know what is a joint distribution, you can estimate anything. That is a very toughest part, how to estimate the joint distribution. In real world, you never able to just estimate this joint distribution. But if say, you somehow know what are the joint distribution and you can estimate the parameters, then you are very lucky, and you will get the best prediction results whatever if you able to estimate these things. But what are the problems in that? The problem is that, for an example, x is having x. Can you write from, like, let's say x1 to xn? There are n different components. So how many rows it will require? So it will have 2 to the power n different combinations. So if it 2 to the power n different combination means up to 0 0 0 0 0. So x can have all zeros also, and likewise x can have all 1 1 1 1 1 up to n1 also. So what is the probability of getting all zeros? So how would you have estimated this? You will calculate the number of rows where you will get all zeros, and divide by total number of rows. That is how we estimated that. But if there are 2 to the power n different rows, it means you, and let's say n equals to 100, it means you are not able to fill that table, because this kind of the huge table is not able to predict. So we have already discussed it. Just go and see that lecture. So how to overcome with this thing? What we did, we came up with a naive Bayes algorithm. The naive Bayes algorithm was like the don't. We have to give some flexibility in our model. We were saying we assume that let's all xi's are conditionally independent. So given a y. So what I am saying, when I have, let's say this is x given y, I can write it probability of x1 x2 up to xn given y. So I can write it probability of x1 given y into probability of x2 given y, and up to probability of xn given y. So this is the naive Bayes assumption. Given a y, I can assume that all are independent. When they are all independent, we know that conditional independence, that could be multiplied in a factor form now. So this is what we are assuming in naive Bayes to so when I don't assume any conditional dependence, my parameter estimated would be approximately 2 to the power n. But when I estimate this kind of thing, my parameters would be 2 to the power n. So from exponential, it will come to the linear. I have already discussed it. Just be careful and see these parts also. So rather now I am estimating by these parameters by multiplying all these factors. For an example, this is my naive Bayes and I want to estimate my probability. So I am calculating what is the probability of yes. So there are total 14 rows. So out of 14 rows, 1, 2, I am calculating how am I counting my number of yes? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 upon 14. It means my probability of yes is 9 upon 14. So what means my probability of playing tennis equals to no, it will be by minus 1 9 upon 14, that is 5 by 14. Similarly, I will calculate what is the probability of seeing sunny if tennis is yes. So these are the number of your rows that I am getting yes, again yes, again yes. So these are the 3 rows, and there is fourth row, and these are again some rows where I get so I'm calculating what is the probability of seeing sunny. So if probability of seeing sunny means I have to focus on the yes only. So this is yes. So sunny is not here. So there are total 9 rows, right? There are total 9 rows. I am calculating my sunny. So this is 1 sunny, 2 sunny, right? So there are 2 sunny. Out of yes, there are only 2 sunny. So this, the probability of seeing sunny when tennis is yes, it's 2 by no. Likewise, we are calculating all parameters. Now, if somebody asks me what is the probability of going tennis, if I see sunny, temperature is cool, humidity is high, and the wind is strong. Now I have estimated it. What is the probability? So how will I calculate it? I will calculate it like probability of sunny, cool, high, strong into probability of yes, right? Divided by probability of sunny, cool, high, and strong. So this is a constant. I will ignore it for a moment, and then my probability of y. This is my probability of y. And I have assumed my conditional independence. So my conditional independence is it's given y, right? So it's given y. So it's given y. So probability of S, C, H, comma, S given Y. So you can write it probability of S given Y into probability of C given Y. Likewise, you can expand all the 4 parameters. Now probability of S given Y, probability of sunny given Y is 2 by 9. So this 2 by 9 comes here. Likewise, now I will calculate probability of C, cool given Cool given yes, so probability of cool given yes, so 3 by 9. And similarly, I will put all the other factors. I will calculate this is the probability with some constant, divide by some constant. Similarly, I calculate the probability of no given this. So how can I write it? It will be probability of no into probability of sunny given no into probability of cool given no into probability of strong given no, divided by some constant, right? Divided by constant. So this constant here, the constant here and the constant here is same, so I don't need to calculate in the both expression. When I evaluate this expression, I will get to 0.206. From here I get to 0.0053. I found that this is the greater than this, so it means the probability of saying no to the tennis is higher than probability of saying yes. So that's why I will say that I will not go to the tennis. You should look all these, how many number of parameters are there and how to estimate it. So smoothing, sometimes it happens here that the probability of getting sunny divided by yes equals to 0. In that case, every time you estimate it, whenever this factor will come, it will make all the expression will convert all the expression into 0, because everything you multiply by something by 0, it will get 0. So if there are some parameters that doesn't exist in the data set, in that case you will get 0 for that estimation. And if that factors come, it will make all the expression 0. To avoid that, you assume some imaginary values for that, and that is why we use smoothing. So we have discussed that also. So discriminative classifier. So in generative classifier, what I have said, in generative classifier, what I have said, that there is I am estimating the probability of y, that is prior, and I am estimating the likelihood probability of y given x, and that's why I can, therefore that can calculate my probability of x given y, my joint distribution, and this distribution can generate artificial data set also. That's why this is called the generative data set. Now I will see what are the discriminative classifiers. So the discriminative classifiers, here we directly estimate probability of y given x. So in generative classifiers, what we were doing, we were estimating probability of y and then probability of x given y. After multiplying these two factors, we were getting this factor in generative classifiers. But in discriminative classifiers, we are not estimating this and not estimating this and not. So we are not estimating these two factors differently and then producing it. What we are saying, we will estimate this probability of y given x and probability of y given x when are directly by the data set, without calculating these two parameters. What we were doing in generative classifiers, right? So this is what we are saying, that we want to estimate this probability directly by the data set. So for this we have to assume some parametric model. Parametric model is saying that we are estimating the probability of y equals to 1 given x is this, and probability of y equals to 0 given x is this. So if we draw this into if we draw this thing into a two-dimensional, let's say this is two-dimensional data, and this is my one class and this is other class. So this will create a linear boundary, and if the number is very closer to it, it will have like one probability. If the number is on the other side, it will have other probability. So what we are doing here, we are just trying to fit the model here, and we are trying to find out what is that linear boundary here. So this is just a parametric model, you have to remember it. So this is just a parametric model, right? It's just a sigmoid. Once you know what it is, like for example here, parametric model for this is y equals to 1. This is my first probability, and y equals to 0. This is my other probability. I am saying, let's say I say that whenever my probability of y equals to 0 is greater than my probability of y equals to 1, I will assign that number y equals to 0. If it is greater, then I will assign this my input x to the y. So it means that when I divide this number probability of y, because this is greater, so when I divide some greater number with some smaller number, I will definitely get the number greater than 1. So it means that when I divide this expression with this expression, so this is by y equals to 0, this is y equals to 1, I divide this expression, I get this equation. So 1 is greater than, I take a log of this, log of 1 equals to 0, and log of exponential is this term. So if we simplify all these terms, what we are saying, that if this term is greater than 0, if this term is greater than 0, then I will assign my input label to y equals to 0, y equals to 0. If this term is greater than 0 here, so if I will plot this, I will plot this, I can say that this is my w0 plus sigma wixi. So this is my this numerator. Every time this term is greater than 0, so I will get from, I will get this I will get here. And because this half is having a higher magnitude, because it is greater than this, when I am saying that when this is greater than 0, this is greater than 0 means that it will be have this probability is greater than 0.5. So I will assign my label to this proportion, and if it is less than 0, then it is less than this threshold, and I will assign my probability to this thing. So this is, we have already discussed it. And how to train it, this is important. Just look carefully. I hope that in the previous lecture it would not be that clear, so I just want to focus on it, how to train it. So the common rule is that we are trying to maximize the likelihood. So likelihood means what is the probability. So this is my likelihood function. What is my probability of y given x? For my first x1 sample, it likewise my what is the probability of y given my x2 sample. So I have to multiply all these probabilities, and my maximum likelihood be when I am maximizing all this expression. So this is my likelihood expression. I am multiplying it for my all my samples. Let's say there are L samples, different L samples. So I want to maximize this function to find out what is my W, and W is again a vector. So I can write this expression as, from here I have taken the log of it. So this is log of this expression. I can write this expression as this expression. Why I can write it? For an example, my data sample is like y1, and there is some x. There is some x1. So this is y1, and y1 is, let's say, 0. And let's say I have y2 equals to 1, and I have some x2 regarding to it. So when I multiply it, so it is like probability of y equals to 0, probability of y equals to 0 given x1 into probability of y equals to 1 given x2, right? I can write it. So now I put one by one. For my first sample, this is my first sample, I put this thing into this expression. What is my y here? My y is 0. So when I put my y equals to 0, this will be 0 here. Now when I multiply this expression with 0, it goes away. What will be left? It will be left 1 minus yl. And what is yl here? Yl is 0. This y1 is 0, right? This is yl. So y1 is 0. So 1 minus 0 is 1. So I will left with this expression. So this expression is here, right? Now I will go to my second sample. When I go to my second sample, let's say this is my second sample, y equals to 2 equals to 1. So when I take y equals to 1. So when I take probability of y equals to 1, let's say, given some x1. So when when I put this value here, so my y1 equals to 1. So this will be 1. When 1 multiplied by this expression, this will remain here. And when I put 1 minus yl equals to 1, 1 minus 1, this will get 0. So my probability of this expression will get 0. So I will, from the second expression, I will left this thing. From the first expression, I was left with this one. So every time I will choose, I have the value of y equals to 0. I pick this term. regarding to probability of y equals to 0. Every time I have y equals to 1, I pick this term. So this is nothing but the other way to write the same thing. This is the same thing, I am writing it in a smart way. So what from here we are maximizing this likelihood function, right? This is a likelihood function. So I'm just taking a log of it. I'm taking the log of this function and I'm maximizing it now. Yeah, you can consider a W0 and X0, but let not be get into the details. So somebody is asking, can we consider here W0 and X0 equals to 1? So we don't, if we need a bias here, I don't want to get into you to confuse into that, but if there is a requirement, you can do that. Not a problem. Even you can do this thing in everywhere, right? So for now, just forget this part of your question and try to focus on it. So what I'm saying that this is my expression, this is my likelihood. I am taking the log of it. This is I'm writing this thing into a smarter way. So this is what I'm getting log of the likelihood. So this expression and this expression are equal. They are no different at all, right? Now I'm maximizing it. When I'm maximizing it, so I'm just doing some algebra. What I'm doing, I'm just dividing these. This is my first term. This is my second term, right? And this is divided. This is separated by this plus. So I'm dividing my both terms by this expression, log of y equals to 0. So when I divide this expression, I will get here log of y equals to 0, which is this expression. And when I divide this term by log of y equals to 0, this will cancel with this. Oh, no, sorry. So sorry for that. So what I'm saying, I'm just expanding it. So it is like 1 minus y. So this term will multiply by 1 and this term will multiply by minus yl. So this is log of minus yl. So this term is yl ln y equals to 1, and this term is log of yl minus. So when there is log or minus log xy, so what you can do, log of x divided by y when there is a minus in between. So because of this minus, this term goes to the denominator here, and this term is the numerator. You can see it by yourself. So this is just a simple algebra. What we have done, we have taken some algebraic form, we have transformed some algebraic terms here. By simplifying, I got this expression. Because most of the times I have seen that a student confused due to this step. So that's why it's explicitly telling that when you multiply this term with minus y and this term with 1, so you will get this term alone. So you are getting, when you are multiplying this term with 1, so with 1 you are getting this term, but when you are multiplying this term with minus y, so this minus y will make this, because this is a log of minus y, right? So this is what yl log of something, and this is my yl log of the same log of something. So this log, what it will do, this minus will make it into a denominator, and you get this term here. Finally you will get, because this is what you are saying here now, this is when you divide this py equals to 1, this is py equals to 1, right? So this is py equals to 1, this is py equals to 1. When you divide this probability with this probability, so this is here, right? It is in the denominator. So it is 1 upon exponential something. So this exponential cancel this exponential, and you get in the denominator this term, because this is 1 here. So you get denominator here, because it is a log of it. Log will cancel exponential, and you will get only this term here, W0. So you will get here this term. Similarly, when you get this is directly, you have put this value y equals to 0 here. So after calculating, you get this expression. Finally, when you got this expression, Now you have to maximize it. So be careful about that. You cannot do it by taking a gradient and putting it equals 0. You cannot do that by putting a derivative and put equals to 0, because it is not a closed form. Now you have to, because if it is not in a closed form, you have to take a gradient. And I have told you what is gradient in yesterday lecture in very detail. So you have to minimize this function taking a gradient of it. So what do you mean by gradient? You take you take a partial derivative with every wi and form a vector of it. When you form a vector of it, you are updating each w with its partial derivative multiplied by learning factor and updating the previous weight. Okay, why we are swapping py equals to 0 given x value? Swapping. It's just algebraic simplification, madam. Just algebraic simplification. We're not swapping anything. They're not swapping anything. If you just don't get confused, because I am going through a very fast pace. If you look it carefully, there is nothing in it that you don't understand. It is just I am saying that a plus b plus c equals to. If I would be teaching it very slowly, I would say that a plus b, first add these terms and then do this term, and then a plus b plus c will be the final term. So I'm not doing it right this way. I'm just saying that it is the final. You will get a plus b plus c. So don't get confused. It is a very simple algebraic form. You will understand it when you see it. So in the previous slide, how did we arrive the final expression? Where did it disappear for for the left part of the formula? I don't understand which left formula it goes away. So here it is, right? So this is the slide. We are having this expression, right? When we are having this expression, we are trying to minimize it. I don't know which one you're talking about. Okay, let it be. It's not a big deal. This is what I'm saying, that this is the function you need to maximize it. When you need to maximize it, you are manipulating it. What you are doing, you are putting it into some algebraic form simplification. When you after simplification, you get this step. You are taking a derivative of this function and taking a gradient of it, and you know what is gradient. I told you yesterday. So after taking a gradient, you are minimizing it. Let's not waste this thing. I have already taken this thing. So this is again what you have seen from this what you have seen from this chapter, that what is the difference between generative and discriminative. In generative classifiers, we estimated probability of y and then probability of x given y. So where it means that I am just generating the joint distribution, and joint distribution means I can generate my artificial data set. But in discriminative classifiers, I am not estimating these parameters at all. What I am doing, I am directly estimating probability of y given x by some parametric form, and that parametric form is nothing but it is saying that this is, let's say this is some class in 2 dimension, there is another class in 2 dimension, and by using, you are fitting this data set by using this parametric form. So you are just drawing a line somewhere that can best classify this thing. So the probability, for an example, you are getting you want to calculate this point probability. When you put this point into this expression, now you will get, say, let's say you get probability 0.9, and when you this is, let's say, probability of p equals to y equals to 1 given x, you get 0.9, and similarly for py equals to 0 given x, you will get 0.1, because this is here at this side of one class. Let's say this is one class, this is C2 class. So directly you are estimating the parameter, and from parameter estimation you are giving the labels directly. Okay. Now the final map hypothesis, optimal Bayes classifier, and gives the algorithm. So map classification, map hypothesis, I already told you so many times what is map hypothesis. Map hypothesis is nothing but it's a Bayes formula, where you need to find out which that from the space of hypothesis. Let there are 100 hypotheses, H1, H2, and up to H100 hypotheses are there. You need to find out given a data, which hypothesis is having a maximum probability. Like what is the maximum probability? So this is written here, which given a data which hypothesis having the maximum probability. So you are taking the argmax. Argmax means you want to find out which hypothesis is that. It will return that hypothesis and assign it to HMAP. So out of 100 hypotheses, what it is saying that out of 100 hypotheses, the hypothesis which is giving the maximum, which is having the maximum probability given the data, that hypothesis you will take it as a MAP hypothesis. And you are ignoring this PD here because this PD, what it is saying, that it is a constant. Let's look this what map hypothesis example again in some detail. So let's say there are three data set H1. There is a sample space, hypothesis space is H1, H2, and H3. So given a data, the probability of H1 is 0.41. 0.4, given the data probability of H2 is 0.3, given the data probability of H3 is equals to 0.3. Now because I am having three probabilities only, so the space is divided by 0.4, 0.3, 0.3, so the sum will be 1, right? So out of these I am seeing that this is the maximum probability I am getting given a data. It means my hypothesis is this, because it is having the maximum probability given the data. And you know what is map hypothesis. Map hypothesis is the same thing. Given a data, which hypothesis is having a maximum probability, that is map hypothesis. Okay, so consider a new instance encountered. Okay. Consider that now if we classify some data set with map hypothesis, is it the best what we are doing? No, we can do much better than that. Even if because this is just a one way to do that. So what you are saying that out of a you have taken best hypothesis, and when you take the best hypothesis, you are classifying some example. If you are taking the best hypothesis out of all hypotheses and you're classifying, are you doing the best now? No, you cannot say that you are doing best. Even there are there is a different way, optimal way, which you can classify the example. For an example, in that case, when you give for an example, let's say some data sample is classified H1 by positive, and by H2 it is classified negative, and by H3 it is classified negative. So there are three hypotheses, and all three hypotheses are classifying it differently. So this is my sample. I feed when I give my sample H1, it gives positive sample. When I feed H2, it gives negative sample. When I feed positive, it is H3 sample. So this is the different labels that my different hypothesis is giving. Now what I am saying, I can calculate the weight of it, because this probability H1 is having 0.4 probability. So I am saying out of 40% of people are saying that this is positive sample, and out of 100, 60% of people are saying that this is negative. Because of the majority, what means here, I am saying that for this X I will give my negative level, because majority of the people are saying, majority of the hypotheses are saying that this sample is negative. Let's see, some question are there. So what is the meaning of the most probable classification not equal to HMAP? That's what I'm saying, right? You should look at this into this example. So the example what I am saying here, HMAP is saying that the sample could be positive. The sample should be positive, right? The sample should be positive, because HMAP is classifying it positive, but other two hypotheses are classifying it as negative. But the optimal classification is also classifying it as negative, where HMAP is classifying it as positive. So there is a difference in it. I hope you understand it. So let's take it. So there is this is known as Bayes optimal classifier. Let's take it example. What is it do mean by weighted? What is that? It's weighted average of all classifiers. Yes, sir. Exactly. So let's see that the problem again. What I was saying, that probably my hypothesis H1 is classifying it as positive, my H2 was classifying it as negative, my H3 was classifying it negative, right? Now what I can say, I am saying that given a data, my hypothesis is 0.4. Given a data, my hypothesis is zero point 0.3. Given a data, my hypothesis 3 is 0.3. So this is my hypothesis probability given a data. Once I have my hypothesis, what is the probability that it will classify it negative? It is 0. Let's say this is the case. What is the probability given a hypothesis H1? It classify positive, it's 1, because I already told you, right? Because I already told you here. This is I already told you that H1 is classifying it as positive, and H2 and H3 are classifying it as negative. So that's why I'm saying, because H1 is classifying it positive, so I'm saying the probability that H1 will classify it as positive is 1. And because H1 is classifying it positive, H1 will not classify it as negative. So that's why I'm saying the probability that negative given H1 is 0. So similarly, I'm saying that H2 is classifying at negative and H3 is classifying negative. So that's why this is 1, this is 1, and other is 0, and other is 0. So how I will do that? So just to find out what is the probability of positiveness. So what I am saying, probability of H1 given data, right, into the probability of plus given H1 multiply. Sorry, probability of H2 given data, probability of H2 given plus probability of H3 given data, and probability of plus H3. So these are the three terms when you expand this expression. So I know there is a probability of data of H1 is 0.4, and probability of H1 given positive, probability of H1 given positive is 1. And here I say that probability of H2 given plus, so H2 given plus is 0, and probability of H3 positive is 0. So because this is 0, this is 0, 0 multiplied by 0, this goes away, 0 multiplied by 0, this goes away, and I will left with by 0.4. So this expression is giving 0.4. Similarly, I will get from this expression, I will get 0.6. So I find out that when I classify my positive sample, I get 0.4 probability. When I classify negative sample, I get 0.6 probability. So I will classify it as negative sample. So that's what it is. Okay. What is Gibbs algorithm? Gibbs algorithm is nothing but because I don't have, sometimes it's very costly parameter. It is a very costly thing, so I cannot do it every time to find out. So Gibbs is saying that don't go and consider your hypothesis, each hypothesis. What you say, you just pick your hypothesis according to the posterior probability distribution over H. So what is the posterior probability distribution over H? In the previous case, it was 0.4 for H1. 0.4 for H1 and 0.3 for H2, 0.3 for H3. So this is 0.3. So this is my distribution. So according to this distribution, I pick my hypothesis and classify X according to that. So according to this distribution, there is a maximum likelihood that I will pick this probability, but it is not saying that you cannot pick this hypothesis also, because it is having some probability. So according to the distribution, you will pick some hypothesis, and using that hypothesis classify that X. What it is saying when you do this is Gibbs saying. So Gibbs is saying just go and don't go for every hypothesis, just to pick the hypothesis randomly according to this distribution, classify the new X according to that picked hypothesis. What is saying that optimal classifier, let's say, is giving E error. So this Gibbs algorithm is not giving twice of than that. So it will be always less than that. So if it is doing 10 error, it will not do more than 20 errors. So the upper bound is 20. So it is not doing more than twice, right? So I will take a short break here, and I will continue it afterward. How to pick according to the distribution is just a random. No, it's just I will take this question afterwards, right?